Okay, well, welcome everybody. We picked an interesting time to have a seminar given the impasse workshop that many folks are involved in. But the timing worked the way it worked, given everybody's busy schedule. And Chris, our usual host, sends his regards and apologies that he can't be our usual host. He's not in this week, so. I'm Tim Schneider, and I'm very pleased to be able to introduce our speaker today, Jeff Bissara. We have a project here that's led by NCAR's community project under the World Climate Research Program, GWEX, core project called Humans in Hydroclimate in the US. And Jeff has been a stalwart contributor and member from the beginning. And it was my great fortune to get to know him through that. And this is actually Jeff's second visit to NCAR. He was a visitor last summer. And I hope, Jeff, there's many more. The collaborations that sort of ensued from the visit last summer, I think, informed some of the work here today. So, and I'm really excited about it. Jeff spent a long time in his career at OU working on impactful extremes and pluvial periods, and you can introduce, and drought. You can share more if you want as you get going, Jeff. But fairly recently, Jeff left the big university and went to the University of Massachusetts, Lowell, and is doing some great things with the program there. He's a department chair and a professor in the atmospheric science.
Yeah, I'll explain.
Okay, he'll explain. But he's doing great things there with the program and growing it and evolving it, and it's very dynamic and exciting to see. And Jeff just continues to be a great colleague and partner and contributor to H2S and many other things. So without further ado, Jeff, I will hand well, you already have the mic, to you.
All right.
Thanks.
Fantastic. Oops, let's go back to the title slide. So before we begin, or as we begin, I again want to extend my sincere and deep appreciation to Tim and others who have allowed me to spend some more time here this summer. Spend some time here again last summer, and that was very fruitful. And really what I'm going to talk about today has kind of grown out of that visit last summer. But I also want to point out my co-author on here, who really is a very important person. That's Jordan Hubbard. Jordan just recently finished up her master's degree at the University of Massachusetts Lowell, and is beginning her work this fall as a PhD student, kind of continuing on with some of this work. And so her and I kind of worked extensively together on this project, but the bottom line is she's done a lot of the work as well, and it wouldn't be possible to even present this. I did ask, actually, if I could present this material as part of a seminar, and she gave me the permission. So I was fortunate enough in that regard. But she's a great person, fantastic early career scientist. Just as a backdrop, she joined the University of Massachusetts only 18 months ago and has already finished her master's degree. So cranking along, and bright, has a bright future. So with that, I also want to, of course, thank some of the other co-authors and contributors to this work, including Jordan Christian, Sophia Bakar, Tim. Some of these ideas have come out literally from, again, the visit from last year, colleagues at the University of Massachusetts Lowell, Venkat Lakshmi, and really the H2US project, Humans in Hydroclimate in the US. There's been just a lot of ideas that have kind of been spurred by some of that research and those discussions. Now, this is where I put my department chair hat on and tell you a little bit about the University of Massachusetts Lowell. So here comes the dog and pony show, right? But seriously, I think, there are some really interesting campuses out there, and the University of Massachusetts Lowell is located just north of Boston, about 20-25 miles. Most have heard of our sister university, University of Massachusetts Amherst, but the UMass Lowell is actually about 20,000 students as well, and it's a public university. We actually are ranked higher in the state of Massachusetts. Actually, we're the highest ranked public institution in the state of Massachusetts, higher than our sister institution at the University of Massachusetts Amherst. They don't like that when we say that, but it is true. At least that's what some of the publications have said. So it's a great campus. It's really near that epicenter of all those all those schools like Harvard and MIT and Northeastern and BC and BU, and we get to kind of live in that bubble as well as the public institution. And it's really nice. Now, our department is Department of Environmental, Earth, and Atmospheric Sciences. We have this nice triangle over there. Basically, we're about science, solutions, and impact. We have multiple degree pathways, including BS and an MS and meteorology. We also have a BA in climate change and sustainability, and that is an interesting, and it's a relatively new degree, and it's growing. Our BS and MS in meteorology is growing significantly. We have about 50 undergrads right now in the meteorology program alone. When you add in our climate change and sustainability, we're approaching 60 students just in essentially our ATMO side, or our atmospheric science side. And we have about 150 undergraduates in our program. About 50 graduate students. We actually have a 4+1 in meteorology, which is kind of nice and a little bit unique. And so a lot of our bachelor students take an extra year, take some extra classes, and walk out with a master's degree in meteorology. It's non-thesis, but they walk out with a master's degree and work a lot in the consulting areas in and around the Northeast. And now in our department, we have four research themes that our faculty work on. We have about 12 faculty. When you add in the adjuncts, about 20 faculty. And we work on extreme events, hydrological processes, sustainability, and biogeochemistry. I work on the top three. I haven't gotten to the biogeochem part. That's really not my thing. So when I was at the University of Oklahoma, I knew a lot of folks. In fact, Mike Eck over here is directly responsible for my dissertation topic, and I wouldn't have been able to complete it without him. That was way back in the day. That's going to date both of us. But I worked a lot on land-atmosphere interactions while I was there. So, OU is known for a lot of things, especially severe weather, but I really had this interest in kind of digging into how terrestrial systems impact the atmosphere and vice versa. But when I moved to the University of Massachusetts Lowell to be department chair, I became a little bit more intrigued about processes that were different, right? I think we all get a little focus sometimes on our local environments, and it was good to kind of get a taste of something new. And the other part is I had never lived in the Northeast before. I'm originally from the greater Chicagoland area, so at least that's north, but the Northeast is inherently different. But what's interesting about it is it is very densely populated. Cities like New York City, Boston, and others, Providence and Hartford. There's quite it's very densely populated, but it's also very densely vegetated, and a lot more so than I thought before, and especially in terms of the forest conditions. It also has no annual cycle in precipitation, meaning it is basically 10 centimeters every month, which means we get about 50 inches of rain every year. And so it's very different. There's not an annual cycle in precip. There's just an annual cycle in temperature, and we get 4 distinct seasons. One of the interesting things about it, though, is it is definitely much more of an energy-limited area versus water-limited. Again, we get about 50 inches of rain, so that's not the problem. The problem, obviously, is incoming solar radiation in terms of some of the processes that we're interested in. And one of the other parts about it is because it's so wet normally, there's really an absence of work focused on drought in the Northeast, because there really aren't many droughts that have happened historically in the Northeast, especially those that have had significant impacts. So of course, that being a challenge, it's like, what can we focus on? Now back to this whole issue of energy limited, evapotranspiration is driven by essentially water availability and energy input and net radiation. And in the Northeast, we certainly have enough water. It's really that energy that becomes solar energy that's the big issue, and that actually becomes very, very pivotal in this issue on drought in the Northeast. So kind of thinking big picture, Don Wilhite and others back in the mid 80s, and certainly it's been reinforced in more recent years, that there are kind of 4 types of drought. And there's almost like a progression of drought. So it starts off meteorological, right? And here's the deal, just about every case, there has to be an absence of precipitation to have drought. I mean, that kind of is like the base, it's the first order. And so I work on a lot of different types of drought, but I will always come back to the basic point that without a lack of precipitation, you really don't have a drought, or at least not in the traditional sense. And so it sort of begins there and progresses. Typically, if you go back and look at the Will Hite papers and others, progresses onto soil moisture and vegetation, right? It goes into that agricultural sector. And then eventually progresses on towards hydrological drought. So this is kind of the order of impacts that you see from drought. And then eventually kind of makes its way down into the socioeconomic side of things. This is, traditional viewpoint on drought, but we'll kind of come back to this as whether, but keep this in mind, we'll come back to this and discuss how that might be a little bit different in the Northeast. Now, there are some sort of events of drought in the Northeast that we can kind of point to, but there really aren't many when we talk about droughts of record. Like in the Great Plains, you can talk about the Dust Bowl of the 1930s, right? Or the 1950s or other areas. Really the major drought of record in the Northeast is really in the early 1960s. And really kind of driven by internal variability of the climate system. Now there was a kind of a significant event in 1980. It was kind of a mild precipitation event, but it was really bad water use, and it led to a lot of impacts in the greater New York City area. And then really, there was a prolonged dry period and some drought from 1999 to 2002 that's kind of been mentioned, but that's really about it. There's not a whole lot of work, again, that's been done, or a lot of studies that have kind of pointed to major drought events in the Northeast, but that doesn't mean that we shouldn't be paying attention to it. One of the reasons why there isn't a lot of work on drought in the Northeast is because, as mentioned, it's already a wet period, or wet place, and then of course, the extreme and total precipitation has basically been increasing in the area. So it's getting wetter, actually, with time, and is expected to continue to get wetter. And we've had a lot of extreme precipitation events, including very recently in the Hudson River Valley, Western Mass, Western Connecticut, had a big event, about a foot of rain in about 12 hours in some of those areas, so major flash flooding. So we've had a lot of those types of events. And really drought frequency, if you really look at it, had kind of decreased between, say, 1900 and on to 2015 in terms of some studies. But yet we are also expecting, as part of a changing climate system, that we might see more of these short-term types of events, lulls in the action, so to speak, in terms of precipitation that manifest themselves as sort of warm season type drought. And along those lines, longer dry periods between precipitation events is kind of one of those things that's expected, and we're definitely expecting that more in the Northeast. And so this is actually the paradox of what we look at when we look at drought in the Northeast, is what does drought even look like? I should come back to this picture later, but unfortunately I won't. But this is actually what drought in the Northeast looks like sometimes. It looks very green, lush, happy, and yet there's no water in the river, right? So oftentimes we see these different types of features that you might see as, like when I stepped off the plane last week, I was like, whoa, it didn't take me long between the, basically the terminal and the parking lot to see, yeah, we're in drought here, right? And sometimes the impacts are manifest pretty quickly. Now, what's been interesting is since 2015, we've started to see something change. And we definitely had an event in 2016 in the warm season, and then two more in 2020 and 2022 that definitely showed impacts, especially on streamflow. And so this is kind of becoming a quasi-normal feature, but it's almost a paradox because it's hard to get people to take drought seriously when everything else looks like this. And right now, even this year, it's a dry year. We're in D2 drought, extreme drought in my backyard, and it does not look like drought. And that's one of our great challenges in the Northeast sometimes. And this might be one reason why we haven't seen a lot of work done in the past, is maybe people just didn't realize that they were dealing with drought. So along these lines, we really wanted to tackle this kind of issue from a scientific standpoint of, first of all, is the hydroclimate of the Northeast changing? Now, there's been evidence of that, or at least the expectation of that. But it's always good to kind of go back and see if the actual hydroclimate is changing. And then sort of how are these warm season events that we've seen in the last decade or so, how are they manifesting themselves within the hydroclimate? And so that's kind of the two scientific goals. So let's tackle the first one. We're going to spend time again in the Northeast. So if you haven't, if you're not familiar with the area, here it is in all of its glory. And really, we're going to spend a lot of our time in New England. But the Northeast often includes New England plus, the 3 states of Pennsylvania, New York, and New Jersey. But New England, and this is really where it's interesting. It's a very densely forested area. When the first European settlers came across into the US, they decreased the forest canopy by almost down to 15% total. And now it's back up over 95% of what it originally was, with the exception of the urban areas. And even the urban areas are pretty densely forested. And that's one interesting caveat to this region of what might be in the future, so to speak. But this is a sort of our study area. We'll spend time here. Now, one way of kind of thinking about evaluating warm season hydroclimate is, so how do you do it? Well, we kind of came up with just a simple way of doing it. We wanted to use observations, and observations are available for a long period of time via co-op data, and that's sort of been interpolated via PRISM. And we have good observations of temperature and precipitation going back to 1895. So one of the questions was, can we use that at least to kind of quantify whether the hydroclimate's changing? We used a really simple approach to it where we for each year, we calculated the standardized anomalies for each warm season. For both temperature and precipitation. And then we just did a simple calculation, literally, of the standardized temperature minus the standardized precipitation. Now you might be going, well, why would you do that? Because we are interested in those periods that are both warm and dry. So negative anomaly in precipitation is a dry year, and a positive anomaly in temperature is a warm year. And so we're looking at what we were looking for is those values that were uniquely positive, right? Now, granted, there's other permutations of this as well, but I will be honest and simply say we wanted to see how large of values of ST, SP, or whatever you want to call it, how large of values actually existed in the climate record for all these different warm seasons. So that's sort of the backdrop, at least from just a simple calculation standpoint. Of course, we did significance testing on this, and I'll show some of the results for the significance testing, and then also did some regression, some Loess regressions, and applied it to the data set. So here's sort of the results of that when we look at these individual states. So we have these at, climate division scale, but they're aggregated up in this case to statewide values, and for each of the 6 states within New England, which, by the way, I think if you add all those states up in terms of size, it's about the size of Colorado, right? So you can think of it that way. Which is great, because I mean, every day pretty much I go across multiple state lines, which is absolutely fantastic and blows my mind still to this day. But so here are those 6 particular states. So again, positive values, where are they? So values towards the top, the values as they become more positive would be years when you would expect to have a combination of increased temperature and a decreased precipitation. You can kind of analogously think of the other side of that, which would be the more negative values would be cooler temperatures and increased precipitation, typically within those warm seasons. So what's interesting is you kind of see some really interesting features that are going on, but of course, just within the last decade, last really 20 years, there's something going on in the hydroclimate that's a little bit different. It's becoming uniquely warmer and drier in the warm seasons in all of these states, in all of these regions. And actually, if we get down to the climate division level, you can really kind of see this. Does that mean every year that it's like that? No, of course not. But you definitely see an increasing trend in this during the warm seasons of increasing warm/dry. And that is really kind of interestingly and uniquely different to the long-term pattern. And what's probably most interesting is pretty much for every state, the maximum values for sort of STSP are nearly all within the last couple of decades. Certainly, usually the top 5, and I'll show some of the more results associated with that. What's also interesting is that in the preceding decades, it was actually a little bit, the mean values were a little bit more on the cooler and wetter period in the warm seasons, but definitely something is changing in the hydroclimate during the summertime and during the growing season. Now, one way to think about this too is, okay, so, all right, you have these composite values that are sort of trending in this direction. How does that break out between temperature and precipitation? Well, sort of when you think about this and just kind of looking at the screen, the values that are temperature being on the y-axis and precipitation on the x-axis, increased temperatures are up, decreased temperatures are down, and then to the left would be decreased precipitation, on the right would be increased precipitation. So the types of years that we are looking at are those that are basically in the upper left quadrant of these plots. And what is interesting about them when we break them out is that you see years like 2016. If we pick on Connecticut here, 2016 and 2020 are in that upper left. So they're kind of getting an equal contribution of both it's warm, way warmer than normal, and drier than normal for this particular state in these particular years. Interestingly enough, 2022 is really more temperature driven. It's really not that much of a precipitation anomaly. And you see that consistently across from state to state. And it is important to point out that you do have these sort of, these values that are clustered in and around sort of the origin, but all of these years, for the most part, are sort of in that upper left quadrant, and that's what we are kind of interested in terms of what's going on. That doesn't mean that there weren't other years that are in the upper left quadrant, but certainly within the last decade, we've had a number of these sort of showing up in that upper left quadrant. And for the most part, they're equally driven by temperature and precipitation, or quasi-equally, but 2022 is a little bit different in that it's mainly driven by temperature. What's also interesting is if we plot these, just do a rank statistic for each of these 6 states. And we just take the top 10 values of STSP, right, that combination between temperature and precipitation, and we plot them sort of from 1900 over here on the left, and more recent years, 2025, 2025 all the way on the right. What is interesting about it is a couple of different things. First of all, there is a high clustering of especially the rank 1, 2, 3, 4 values that are over here on the right-hand side. Meaning these values that are in that upper left quadrant, a lot of them are showing up in the last couple of years. And what's also interesting is that there was a group of them that were occurring, say, before 1960, and they were more widely spaced, and this probably is more internal variability of the climate system. And then what's also really interesting is there's a gap from about 1960 to about 2000, about 40 years where we really don't see any of these extreme values that are in that upper left quadrant of those plots, which really is also coincides with sort of a much cooler and wetter portion of the hydroclimate. So we have seen obviously some different changes that are going on, but what is really interesting to us is the clustering for all the states of basically something is happening because we're starting to see all these values appear in the upper left-hand corner in more recent years. But there are some interesting things happening in the hydroclimate of the Northeast, I guess is probably the better way of putting it. We did do the statistically significant, or the statistical significance of these. For the 2016 and 2020 cases, all the states were statistically significant. We did it by a couple of different ways of looking at sort of the full data set, but then also using a baseline data set. And what is interesting is that 2022 was really more isolated to Massachusetts and Connecticut. And we'll look at that from a drought standpoint here in a second, and you'll maybe be able to understand a little bit more why. What's also interesting is we did all the other states of the Northeast as well. None of them actually, a lot of them didn't show the same types of trends. So New England is behaving differently than the Northeast. And if you ever needed another explanation of why New England is different than New York and Pennsylvania and New Jersey, here's another one from a hydroclimate standpoint. It's just not the same. And there's reasons why those two regions don't always get along, I guess is probably the best way of putting it. It's not just about the Yankees and Red Sox, I guess, or the Jets and the Patriots or whatever. So kind of moving on though, so the hydroclimate is changing, and hopefully, that's just a kind of a simple analysis of it, but the hydroclimate it definitely has a signal that is changing. And these warm season signals are definitely beginning to trend more towards the warmer and drier. So let's get back to a quote that I like to use, and I'm going to quote myself, actually, because I managed one time to put this in a paper that I was writing on flash drought. And there's always arguments about drought and what drought should be, and what is drought here, and what is drought there, and so on. But the argument that I like to make is it's just not the same. Each individual case is different. There are multiple categories of it. It shows up and manifests in different ways. There is something like snow drought, and there is something like precipitation. And sometimes it's slow moving, and sometimes it's rapidly developing. And really, not all drought is the same. And I was glad when they didn't make me change that line in the opening part of a discussion I wrote as part of a paper published in 2019, because I'd like to go back to it all the time and really kind of point out that it's not the same. And what we're seeing even here in New England is a little bit different. Now we're going to use some of the plots, hopefully you've seen the Drought Monitor before, and we talk about D0 all the way to D4. So we'll see some maps and some plots here of drought using the Drought Monitor. So there's kind of the scale. Here's those 3 different years. And again, this is drought focused by the Drought Monitor, focused on the Northeast, although it does actually take into account Delaware, Maryland, and West Virginia as well in these plots. But looking at New England, 2016, near peak had D3 drought, actually extending along a long corridor along the down east coast. And then also similar types of conditions in 2020, with really, severe drought extending all the way up throughout most of New England, including all the way up into Maine. 2022 was a little bit more isolated to Massachusetts with D3 drought, and there was D3 drought in 2020 as well, 2020, but D3 drought really in 2022, but it was really kind of isolated a little bit more in a smaller pocket. By the way, that 2022 drought, there were 2 major droughts going on at the same time, one in the central part of the US and one in Europe. And so you had these huge droughts and then this little itty bitty drought in New England, but it was impactful. All of these were impactful in different ways. So kind of, what the point here being is that even by Drought Monitor standpoints, these were pretty significant events, at least on the regional scale across New England. And there's also another reason why we didn't quite focus on the greater Northeast area, because some of these, like 2020, 2022 really didn't have as significant of impacts across, New York and Pennsylvania and New Jersey, although it is there. So flash drought, if you were here last year, I gave a talk about flash drought and sort of how it manifests itself, and I think it's becoming much more widely recognized as a pretty significant, impactful extreme. And basically, you kind of have this progression of clear skies, warm temperatures, higher winds, and basically leading to desiccation of the land surface over a pretty short window of time. And again, it's always first order of lack of precipitation. You can't have any type of drought. But what sets flash drought apart is you kind of get this rapid intensification. It's kind of like hurricanes. You have multiple types of hurricanes, right? But there are those other types of hurricanes that have rapid intensification cycles associated with them. And it's kind of similar, it's analogous at least, when we think about drought and flash drought. But what ends up happening is typically there's just a really hostile atmosphere, really hot, dry, windy, and it really leads to desiccation of the land surface pretty quickly. So the question was, were all of these flash drought events, right? Well, there are a lot of metrics that have been developed and produced to kind of try to grab on flash drought. There's the evaporative stress index, or the evaporative stress ratio. There's EDDI by by Hobbins and some of the NOAA folks here in Boulder. They've developed that. We've kind of, Martha Anderson worked on the evaporative stress index. My colleague Jordan Christian and I really worked on the standardized evaporative stress ratio. There's the SPEI and the sort of the standardized precipitation index. All of these can be useful tools. And what's really been interesting is there's been a lot of emphasis, especially on the top here, about using sort of this evaporative demand type of perspective that really kind of clues us into being able to identify flash droughts. Well, there's a problem with that I'll show here in a minute. And as basically these all point out to, as the evaporative demand goes up, the actual evapotranspiration goes down, and the greater the distance between the two of those really kind of clues you in that something is happening, especially in the land surface. But Pendergrass et al. Also had another example, to identify flash drought, and so in this case, this is actually what we use, because we found that when we were using some of those other tools, it really wasn't showing up, and we were kind of confused as why at first. And it turns out when you can use the Drought Monitor and to identify flash drought cases, and so we actually did, and in all 3 cases there was actually flash drought by the Pendergrass method that occurred in each of these areas. So it was rapidly developing. We certainly saw that in the Drought Monitor. The categories were increasing pretty quickly across a couple of weeks and then stayed there for a few more. But there's also an interesting aspect of this, and I kind of showed it with that one slide, is that oftentimes we see drought showing up in the streamflow and in the hydrologic processes, especially in New England. And there's really been a gap in the literature. Most of the research is focused on the agricultural side, right, and that agricultural drought. From a flash drought standpoint. And I will honestly say I'm part of that problem, having worked in the area, of really saying, hey, this is kind of limited in that zone. And so I'm here to eat a little humble pie along the way, in that we kind of neglected some of the hydrologic processes. There was this kind of thought process by me and others, I will say, that maybe kind of dismissed and diminished the fact that we would even see these types of features showing up so quickly in the hydrologic portion of the drought spectrum. But some of the more recent research by Bakar et al. And Singh and Mishra have really kind of pointed out that there are features that seem to be flash drought related and look like flash drought, but they're showing up in the hydrologic cycle, especially in the streamflow. One thing we also did, of course, is to go back and look at this. Drought is always a first order precipitation deficit, and so we actually went back and looked, and sure enough, all these cases, if we look at precipitation accumulation over the year, basically the black line being climatology for all these states in the 3 years that are plotted, you see that they're almost always below the line. There's sort of the one case, Maine was an outlier in 2022, but all of them had significant precipitation deficits, and most of them manifesting themselves sort of beginning in April, but certainly April, May, and then into June, there were some pretty significant precipitation deficits. So again, these are all drought periods, and they were driven in part by a lack of precipitation. Surprise, it's drought, right? That's what we would expect. Okay, so let's sort of moving on from there. One thing that was interesting though is, so droughts occurring, well, what's happening in the land surface? Now, one of the problems, and this is actually a problem that sort of struggled to deal with, having worked in Oklahoma for as long as I did, we would just put surface flux towers up all over the place. At one point there's a piece of land at the Grazing Lands Research Lab in El Reno that has 17 flux towers on it right now. You didn't know that. We should talk because I have good data for you. But they have basically a flux tower on every different type of field and grass system of the region. So over croplands and over grazing lands and mixed pastures and managed pastures and a whole shot. So I was so used to having all sorts of flux tower observations to look at ET, right? Well, that's not exactly the case once you move to the Northeast and you move to New England. And there's really only one in New England. There's 2 flux towers, but only one of them has a really long data set, and it's the Harvard Forest. And the Harvard forest has this great above canopy system, in canopy system, below canopy system that they actually have been continuously using and monitoring with surface fluxes and other processes for years. So one thing we wanted to do is, okay, well, let's take a look at at least let's take a look at the ET over the canopy at the Harvard forest, which is pretty, it's pretty representative of a much broader area. And let's take a look and see what was happening in the canopy, or at least at the canopy top during these drought periods. Along those lines, we also wanted to at least kind of get some perspective on broader areas, so we used Era 5 data to kind of look at some of those, and we also calculated, obviously, reference ET, because we were interested in some of these values, the actual ET and the reference ET, to kind of look at the evaporative stress. And what was interesting was, for the net radiation, it really kind of highlights this. Remember I said the New England is an energy-limited environment. So what happens during drought and a lack of precipitation? Climatologically, sun comes out, the clouds disappear. And actually that's what we see in all these cases, is with the blue line being sort of climatology of net radiation, and sort of the orangish line being the actual obs for each of those given years, and looking at these different warm seasons. For the most part, during the entire warm season, there's a couple of days in there, but for the most part, the warm seasons had above normal net radiation, which makes sense, right? Lack of precipitation, lack of clouds, increased net radiation over the region. So that sort of follows the trend that we would expect. What was a little bit interesting, though, is when we started to look at the ET over the top of those canopies. This is actually this is the evaporative demand. Sorry, before I get to the ET, I was getting ahead of myself. But the evaporative demand, because again, it's clear and increased net radiation, temperatures are hotter, the environment's drier, as you would expect during drought periods. The reference ET is above the climatological mean, which is, again, what we would expect to see. That would almost always be what we would expect to see. The evaporative demand was increased during these periods of drought. What we didn't expect to see, well, that's the fun plot. That's typical, right? That would be what we would expect. What we didn't expect is that when we went back and we actually looked at the latent heat fluxes, the latent heat fluxes were also above normal, considerably above normal for at least 2 of the 3 years, especially during large portions of the period of the warm season. And usually during drought periods, we would expect to see the latent heat flux drop dramatically. And that's not really the case. Now, even here in this one, and we actually have I should have put the newer plots in that actually have the ranges and 1 standard deviation. Here it's running close to climatology and a little bit lower, but these two are definitely above climatology, which is, again, a little bit not what we would expect. We would expect to see, in most cases, the latent heat flux crash once drought really became manifest. And so these metrics that use the evaporative stress to identify drought are not working, because you expect to see the difference and a decrease in the latent heat flux with a sort of increase in latent heat flux keeping up, essentially. The actual ET is keeping up with the evaporative demand. We're not seeing a gap develop, and we can't use those metrics. They don't work, actually, is a better way of putting it, to identify rapid intensifying drought in this region when that's happening. And so we went back and we also looked sort of larger scale. Okay, we're seeing this at the forest, but do we see this over a larger area? And so we used MODIS data and used the Land Surface Water Index. And, Jordan Christian and I actually had kind of developed another tool using MODIS data to identify, to be able to essentially identify flash drought in the land surface using vegetation data. And we expected to see that would show up. And what we actually saw was something different. And what's really interesting about a lot of these cases, it might be a little hard to see here in some of these plots, but especially 2000 is a really good example, but even 2016 has it in there, and for the most part, 2022, we actually see an initial green up. So as the drought really gets rolling, as the drought really gets rolling across the region, we actually don't see, either we don't see much of an impact in the vegetation data and the vegetation conditions, or actually we see the opposite of what we would expect. Because typically, you expect everything to start to dry up. Vegetation starts to suffer, wilting, get near that wilting point and so on. We didn't see that. In fact, we see a greening up of the vegetation. So that is inherently a little bit different. And even during all three of these cases, especially during the peak portion of the drought across most of these regions, we actually see either normal or above normal greenness values in the vegetation, which is, again, a little bit surprising. And definitely, we're not seeing a vegetation response. In fact, we're seeing the opposite of what we would expect. So then we get back to the stream flow part of this. And we have one thing that is great about New England is I think every creek, tributary, river, everything has a stream gauge in it somewhere. And that is what's fantastic. And a lot of groundwater wells as well. And so there are some methodologies to kind of tease out the data and identify stream flow -- drought. And what's interesting is this is 2016. So let me put this into perspective. This is going from the beginning of the year, the beginning of the warm season, April, and then going all the way to basically November. And this is stream flow. Now this is every single gauge in each one of those states. That's a lot of lines. That's what all these lines are on here, right? So you get the full suite of all these lines. And then the black line is sort of the mean. It is the mean of all these gauges for each one of these states. And what's interesting is these are percentiles, so 50th percentile basically being the mean. So this is looking at this as from a percentile basis as you go from across the warm season for 2016, and then all of these different gauges. And what's interesting is almost all of these locations, going April, May, are at or above the 50th percentile, meaning there are normal amounts of stream flow. But almost immediately after, they all drop pretty substantially. And these are percentiles, right? Based on essentially the local climatology for that time of year. And what's interesting is all these states, all these gauges, not all of them, but most of the gauges, especially here like in Massachusetts, but even in Maine and some of the other states like Rhode Island, you see them all drop below the 20th percentile. And that's getting into a pretty significant stream flow deficits at that particular point in time. In fact, a lot of them were at or below the 5th percentile, which is really quite significant in terms of the amount of stream flow. That means we're not seeing drought in the vegetation, but we are definitely seeing it in the hydrologic side, and it's getting there very rapidly. Now, this is 2016. If we go ahead and look at 2020, you see something similar, although you could definitely see where there was an intermittent rainfall event, especially in some of the regions. But it definitely, even afterwards, it continued on, again, starting above normal, and then rapidly decreasing to below normal, and actually in some of these cases, again, getting down below the 5th percentile in a lot of these gauges across the region there in 2020. And then again, even in 2022, which is a little bit more temperature driven than precipitation driven, we still see the same types of things. So what's, again, crazy about this is that we're not seeing the impacts in the vegetation, but the stream flow is literally bottoming out at the same time, which is interesting because oftentimes when we deal with stakeholders and they want to know when drought is happening, they want to see it. And oftentimes the way they see it is what's happening in the environment immediately around them in the land surface and vegetation. And oftentimes what we're seeing is very green, lush vegetation. We're in drought right now in my backyard, and it does not look like drought. It's very green. But if I go down to the river where I want to go fishing, or the creek, or the Nissitissit River is my favorite river to fish, there's no water in it. And it dropped dramatically earlier this summer. So 2026 looks like it's going to be another one of these cases. I will, as an analogy, I went to the river, and within 1 week, the river dropped a foot. You could actually see it dropped at least a foot in 1 week. And part of it is, okay, so what's going on with all these processes? So again, back to the normal drought, traditional view. And I'm going to pull up a quasi-Mike Eck type graph here. And I created this one. But this is basically the drought life cycle as a coupled land-atmosphere system. And really you get these nice dynamics that happen, right? As the atmosphere gets drier, the land surface becomes more desiccated, you get more sensible heating, then dries out the boundary layering, you get this process kind of rolling on and from development to intensification and persistence. And land atmosphere feedbacks play a really important role in the development of these types of drought events. But what we're seeing in the north, and really this does show up in a lot of other places. So these are some of those really significant flash drought events that have happened in other locations, like 2012 and 2017, 2016, 2022. You see this manifest itself real ugly, in an ugly form in the vegetation a lot faster than maybe what you would normally expect. We're not seeing that certainly in the Northeast. And again, that gets back into the vegetation response to this study, was that we actually were seeing the opposite. We're not seeing those same types of conditions you might expect in other vegetated regimes. You know, part of it is because when we look at drought, and this is from Wang et al. In 2023, when we look at the sort of the extinction depth of precipitation or of water for different types of regimes, you know, bare land versus, you know, shallow rooted plants versus, you know, trees like in New England, you know, the two on the left are really dependent on rain-fed infiltration, and those extinction depths are relatively shallow. And there's actually an interesting dry gap that tends to develop between that and the groundwater, but the deeper vegetation, or some of this vegetation, like these trees, have an opportunity to extend the rooting depth into that zone and actually be able to maintain itself. And so in an energy limited sense, you know, once the sun comes out, they're still able to access deeper water and green up. And we're not getting, you know, we'll go, okay, so now it's not really a coupled system, which is maybe true. This is even more of a MICA graphic. But what's interesting is in the typical evolution of, say, flash drought, we do reach a tipping point where essentially soil moisture and ET kind of decrease, and then sensible heat, air temperature, and vapor pressure deficit decrease. There's a window, sort of a transition zone and a tipping point that gets reached. And what I'm going to argue in some ways, I think, is what's happening is the vegetation, because it has a deeper rooting depth and get into that water table, is able to sort of hold off that tipping point, at least on the vegetation atmosphere side of things. But what is happening at the same time, it's also by getting its roots deeper into the water table, it actually is doing all that extraction, but then that's lowering the entire water table, and that's one reason why we see all the stream flow begin to rapidly decrease all at the same time. So that's at least the working hypothesis that we're going with, which is inherently different than the typical drought propagation. So maybe in drought and maybe this new regime that we're dealing with in a new hydroclimate, this is kind of the propagation of meteorological drought to the hydrological drought. And then on to the agricultural eventually, if it stays there long enough, and then eventually into the socioeconomic. This one at the bottom is really important and really hard. So I work with a group called Mass Rivers. And they struggle because they're like, right now they're like screaming drought, drought, drought to anybody who will listen. And everybody's like, well, it's mid-80s and everything's green. So what are you complaining about? And it's like all the water is disappearing in all of our surface water systems, right? And so sometimes when we think about what they call the hydroillogical cycle, sometimes getting people to actually recognize some of these features is difficult. And it is difficult to see drought when everything around you is actually pretty green, like my backyard. So again, the key points, we did see some of these we definitely saw these droughts that were happening, and they definitely had more of an impact in the hydrologic side than they did in the vegetation side. We're actually seeing some processes that are fundamentally a little bit different. So when I talk to folks like at the Drought Mitigation Center and those who make the Drought Monitor, they're actually pretty curious about this because they would expect to see something different in the indices that they're using. And so this also does lead to bigger questions about maybe we should be looking at some of these energy limited areas to look at different ways of how drought manifests itself, especially even in these rapid intensification phases. And it's really important to go back and look at that stream flow. That stream flow drops very fast in a lot of these systems, going from above normal to well below normal really quickly. And the other part of this is that, you know, the hydroclimate in New England specifically is changing. And it is definitely moving into a different type of regime in the warm season, which is inherently interesting in an area that we would expect to see, and we do see maybe increased precipitation, yet we're getting our warm seasons to become warmer and drier at the same time. So it's kind of a little bit of an overall paradox. And again, this is a confusing issue to stakeholders when we talk about these types of issues. And again, the interesting aspect of this now as well is we've been pushing this boundary, I think, at times with these drought cases of getting to a point where we're getting closer to having a greater wildfire risk. We've had a number of small fires that have kind of begun to manifest themselves at the tail end of these in the fall. Now, this is the other part of this that's really difficult to kind of, when we deal with people and the stakeholders in the region. Because drought does a really amazing thing to the vegetation canopy. It makes all the colors pop in the fall. So there are actually a lot of people that want to have a little warm season drought to have a better leaf peeping in the fall. Seriously. And if you don't believe me, just go try to take the Kangamangas Road in New Hampshire in September, late September. It's literally a parking lot over about 50 miles. That's how many people are there, right? So it's big business, right? And but yet at the same time, with that comes increased wildfire risk. And this is actually one of our big concerns, because I think we're starting to see in a lot of different places that wildfires aren't just constrained to the west, right? They are happening. They happened in Southeast earlier this year. They've been up in the boundary waters of Minnesota this year. I expect maybe North Carolina here soon, based on their conditions. And it's a matter of time before this region probably has a significant event moving forward. And then one other thing is actually one thing that's kind of fun and I like to do is, you make something that's really useful like we did with Caesar, and then you find out that in some cases it just doesn't work. So back to the drawing board from an index standpoint, what do we really do in terms of developing tools that help identify these features in the future? And so, again, let's kind of skip that, and we'll just kind of go to questions. Obviously, it has big impacts on stakeholders, but I've kind of already mentioned that. So, thank you for your time. Any questions? I left a little time.
I've got the magic cube.
Okay.
But before I forget, again, I was going to say this at the beginning, but we're going to be heading over to Twisted Pine at 5:30. If anybody wants to come over, hang out with Jeff and others, please feel free to join us, 5:30.
Good time for a beverage.
For a while. Yeah, I think we're going to need it, and it's nice and cold. So,
and I think actually the power is getting turned off at 5, right? Is that correct? So.
Yeah, so we'll need to vacate FL2 anyways. So, and for folks online, if you're in town, please feel free. So we've got, I think, we'll go Mike and then Ethan.
Okay, I got several questions, but we can talk to him about them over beer. Actually, one thing that's not related to drought, I was interested in your climate change program at your university. Did that get targeted at all in some manner, or was it under the radar?
So this was one of my brilliant ideas when I showed up in the fall of 2023 to change our BA from an environmental science BA to climate change and sustainability, because actually our campus is the #1 sustainability university in like New England. It's got all these like it's platinum LEED and all sorts of things like that.
Sure.
So sustainability and climate change are really big deals. We actually have on campus a climate change initiative team. Actually, it's a group of faculty as well, and so we have this whole institute plus all this. So it made sense, right? And then the election happens right at the time when the degree gets approved, and I'm like, well, this ought to be really interesting. We officially started that program just this last fall, and now we have at least 10 students in the program, which tells me something a little bit, is that and Massachusetts is a bubble, certainly, and most of our students are actually Commonwealth students anyways. And there's a lot of work that's being done in these areas. And of course, in Massachusetts, they have a whole initiative right now at the governmental level to become the climate tech capital of the world, right? And so there are actually a generation of jobs in this area of climate change and sustainability, and it's being fueled by just the local system. So while we are worried, while there is concerns about something that might be happening outside the bubble, inside the bubble is actually not a bad place to be right now. And so we're seeing students that are actually enrolling in the degree program and wanting to be a part of that.
Okay, kind of an in-your-face degree.
I wouldn't say that, especially since this is recorded. I think it's a timely degree for those who are willing to stay in the game.
Well said.
But I have to admit, I had my doubts at first. I was like, did we just make a real big mistake?
Thanks. So So I was going to ask if you have looked at OpenET and what that tells you, but you mentioned stakeholders at the end, and that got me thinking about something else, which is what are the like agriculture, dairy, similar industries in New England think about this? Because it seems like if productivity is going up, drought might be good for them.
Yeah, so that's a really good question, right? Yeah, this is where we get one person's calamity is another person's treasure, so to speak. Yeah. And there's some great orchards and dairy farms and all sorts of things like that. And I tell you what, I'm a big ice cream person, so there is literally an ice cream stand, if not more than one, in each town. Like, and it's that whole concept of Ben and Jerry's is manifest every 10 miles, really, and where I live, and I love it. And I think on the agricultural side, because we don't see it drought manifesting as much in the canopy of the forest canopy, but I do think when we get down a little bit more into the individual farm scale type features that are subgrid scale that you can't really recognize as well, the impacts do sort of manifest more in the negative way. And there's not a lot of irrigation there either, because it's typically a very rain-fed area, especially in the summertime. So there are some concerns certainly, and in the Connecticut River Valley, which is sort of that part that runs basically from central Massachusetts down into Connecticut, there's a lot of just broader agricultural areas. And if you look on some of those maps, you can kind of see those are some of the first areas where you start to see it's not greening up as much as some of the other areas. So I think that's one of those questions that's still to be kind of looked at, is when we look at the different types of systems that are there on the agricultural side, are we seeing some of those impacts? But I think on the orchard sides, like the apples and some of those, huge apple producing area, they don't seem to mind nearly as much as some of the other more cropland type of systems.
Maple syrup.
Yeah, maple syrup, just if you want a good Honeycrisp apple, they're good.
Hey, yeah, great talk. This is James Pinto. So I was curious about 2022, because in terms of the vegetative index, it looked like it had a different response in your maps, that it actually was showing an impact.
Yeah.
Is that because temperature was so much a larger anomaly that it was really impacting things?
And I think that each one of these cases is going to have a little bit of individual variability associated with it. And I think that one, because it was a little bit more temperature driven, may hint at the fact that, you reached the critical tipping point at some point in the temperature side of it, and it definitely had a little bit more impact on the canopy. But we are still looking and digging through cases. It looks like 2025 was another case, which was last year, and here we are again in 2026 in the same regime. And so when we start thinking about this, that would put us at like 5 years in the last, or 5 years in the last 10 that are kind of in that upper quadrant now, which is, we're getting more. From a science standpoint, it's like, hey, we're getting more cases. And I like droughts. So I'm like, all right, let's get more data, right? More data, better data, or more robust results. And then the people I work with at Mass Rivers are like, you can't get a kayak into this river anymore, right? And our recreation systems and our water systems, and when are some of and all the communities now have gotten into watering restrictions, which is crazy because everything's green anyways, and yet they're introducing all the watering restrictions because they are concerned more about municipal use of water and having available water. So it's really interesting. Yeah.
So, thinking about your comment about how the trees access like the deep water. So I have one comment about how generalizable is that for the climate type that New England is to other areas of the world.
Yeah, no.
So I'm thinking specifically in Europe, they have a horrific drought right now. And so there's this sort of infamous picture of like fields in England where you see green trees, but then like fields that are totally brown. Right. And the middle of the church is in the field and surrounded by brown, but green trees in the background. So it's got to be the same kind of regime in places like, Northern, Central Europe. So I think there's a lot there in terms of like generalizability. beyond New England that is really important.
Yeah, and that I couldn't agree more with you. In fact, Jordan, when we were having conversations recently, she's like, I want to look globally at all the energy limited areas and see if we see similar types of things.
So the second comment is that I think if you don't have a good index, then you have to invent a new one. And then the question is, what do you want the index to get at? And really, you need to get at something that is excluding the deep water moisture, so soil moisture in the vadose zone, something like that.
Yeah, something in the critical zone for sure. Absolutely. And that is a real good point as we kind of move along.
So they should invest in soil moisture monitoring.
And that when we start looking globally, that becomes a challenge, right? And I think that's one of the other issues that we'll face as we kind of think about this in other zones. One thing that is nice about New England, I didn't mention it, we actually have a lot of groundwater monitoring wells. And in some of these cases, these cases, we haven't finished that part of the analysis, but in some of these cases, we are seeing up to 2 meters of groundwater change in a matter of about 2 to 3 months. That's a big, so what we're seeing even in the water table is making its way even into the groundwater systems. And I didn't put it in here because we haven't finished that analysis, but there are some preliminary results that show that this is actually happening in and through the vadose zone.
Eventually we will get to a tipping point where the trees won't survive.
That's right. Yeah, and it's where's that tipping point located? And then how, if it lasts long enough, maybe we'll get there and then we get to a real critical fire situation.
Okay.
The only thing I was going to make a quick comment on is, well, I was just at a seminar this morning with USGS where they're talking about some of these same issues. In fact, this decrease in base flow under these warmer, drier conditions than what we saw in the past. The other thing, and thank you for the plug for eco-hydrologic processes, which is what's driving all of this, which I think is really critical that we're not always representing super well. But the last point I was going to make is that this thing that you talked about with this drop in streamflow, that's a really big deal for water quality.
Absolutely.
Which is a big deal in the Northeast. So I think connecting this research to water quality is really going to be important.
Yeah, I couldn't agree more. And what's interesting about the Northeast is Northeast has a history of really bad water quality, but it's by coming out of that.
Yep.
But when we start exposing everything to what was still there, yeah, you potentially can reintroduce all those old issues.
Salinity coming in from the coast.
That's right.
And then when you have more groundwater influence, you get everything that's coming in from the groundwater, and then the temperature too for all the critters that are trying to live there. So yeah, great, thank you.
You're welcome. Thank you. Appreciate that.
Okay, I didn't see any questions online, and we are over time, so let's thank our speaker one more time.
Thank you. Thanks. You got it. Appreciate it. Have a great day, everyone.